Alors, cette équipe s'appelle Teadusbuss. Ils viennent d'Estonie, donc ils vont nous présenter plein de sciences différentes. Merci d'accueillir Vootele et Oskar.
Hello everyone!
Bonjour Genève, je m'appelle Vootele.
Yeah, and my name is Oskar.
This is where the French ends.
Yeah, pretty much. So, we're two physics students from the University of Tartu, here with Teadusbuss today, as you heard. And Vootele, what do we have in store for the good people of Geneva today?
Well, I could just, tell you, but I think it would be much more interesting if I showed you first. So, please do direct your visions to this rectangle on the screen and let's see what happens. So, Oskar will put the setup just right, and now, 1, 2, 3, et voila!
Whoa. So, this is something called Schlieren imaging. And as you can see on the screen right now, we can actually see air move. And we can also see air interact with different objects. And for this very reason, this is something used a lot by places like NASA, Boeing, Lockheed Martin. Basically, anytime you need to make something move through air real fast, this is your best friend. But let's be a bit more precise, because if you're paying attention, you can mainly see the hot air move that the candle is heating up. And that is because hot air is lighter. It is less dense. And why does that matter? Well, that matters because of how light refraction works. You see, when light moves from one environment to another, it changes direction. I have some friends here. It changes its angle a little bit. So let's say we have light moving from the white environment into the blue environment. It's going to change its angle. And how much it changes its angle is something called a refractive index. And different densities of air actually have different refractive indexes. And this is the main thing that helps us see all of those shadows there. So right now we're seeing, in a second, we're seeing a candle work its magic. But I think that cold should work just as well, shouldn't it?
Yeah, so right here we have hot air being visible with Schlieren photography. And it would be logical to assume that we can also see cold air as well. So right here I have a cup of liquid nitrogen, which is, really cool stuff. Really cold, I mean. And, thank you, Oskar. If we were to pour it in front of the test area, as logic follows, we should be able to see it. So let's conduct an experiment. This is this cold air, and yes, we can see cold air just falling down like that. And of course it is falling down because cold air is denser than normal air, and this is why we can see it falling down. You may also notice that this cold air is much more darker than the hot air was. And this is because the cold air is also condensing out little droplets of water from air. And we can see those water droplets as those really dark spots. But more about that later.
Yeah. But now a question for all of you. So we've seen different temperatures of air interact a lot with each other. But let's say we blow some room temperature air in front of our mirror really quickly. Would we be able to see that? Raise your hand if you think yes.
Okay, so you think room temperature air should be visible. Raise your hand if you think no.
Okay, and if you didn't have an opinion, raise your hand now. Okay, very good. But I think there's only one way to find out.
Yes, through science, of course. We need to conduct an experiment. So right here I have a regular balloon. I will fill it up with air. So, this balloon is now filled up with air from the surrounding environment. This is basically the same temperature and basically the same chemical composition as this tent air. I will blow out the candle, and if we were to be able to see just fast-moving air, if I release the balloon in front of the test area, we should be able to see it. So, let's check it out. So, Oskar is setting up the device, and
should be good. No.
No, not really.
Just some slight flickering of body heat.
Yeah, that's...
Yeah. But let's say we have something very heat sensitive.
Yeah.
What do we do?
So we can't use room temperature air, we can't use hot air. we should use some gas that has a different refractive index from normal air. So right here I have a balloon filled with helium. And as you might know, helium is a much lighter gas, and thanks to this it has a lighter density and also a different refractive index. So, as logic follows, if we pass this gas through the test area, we should be able to see it. So, now let's check it out. Okay, were you able to see it?
Much better. Now, as all of you might have noticed, I was fiddling around with some gadget. We have like a big metal thing there. So what is all of this? Why do we need all of this?
Yes, I will give you an in-depth explanation of everything here. So, how does it work? Oskar told you before about refractive indexes. When a light beam goes from one environment to another, it changes its angle. Those angles are not equal. So let's say that we have this test area and a cloud of hot air in the middle. Let's say that this is the cloud of hot air that the candle created. If we then have a bunch of collinear white light beams going into this test area, like this, as they are shown here, and some of them will hit the cloud, some of them will go over it. Then the ones that go through the cloud, they will be, of course, refracted, as you might remember. And the other ones are not refracted. And once they leave the cloud, they are refracted again. So you can see how their angle is the same as before, but they are now bunched together. So in effect, the difference in air density actually caused a difference in light beam density. So now, finally, how do we make it a visible image? We need to put a filter in between. So let's say that this is the image that the cloud created. Some of the light beams were moved away from their original course. Some of those light beams will hit the green filter pictured right here, and the other ones will go over it. And the green filter, of course, colors the white light beams green, and the others stay white. And this is why we see those shadows appearing on our setup. So our whole setup is pictured here. This right here is the point light source, which shoots out light beams like this. And then they hit the concave mirror, a very precious concave mirror, which was confiscated at the Tallinn airport. Finally, we got it back.
I think they were jealous.
And the concave mirrors, they focus the light beams back into this apparatus, and the apparatus has this, before mentioned, green filter inside of it.
So, this is all fascinating science. And now that we know how all of our system works, let's see what else we can do with it. So, as you might remember, Vootele mentioned water before. And water has a different refractive index as well. So, why don't we see how different it is? Because, as we know, a bubble is mainly just a very thin layer of water. And one second, yeah. It looks a lot prettier when it's zoomed in, so. And okay, yeah. So, as we can see right here, it's got some very different patterns. That's because of the water moving around. And but you might say that, sorry, oh, the bubble broke. That's fun. 1 second. Now, you might say, but I can see through it. Well, if I were to turn it on the side, you can start seeing water collect at the bottom, and that is a dark patch you cannot see through, because water's refractive index is sufficiently different that we cannot see through it with the system. And keeping on the same theme, let's check it again with the colder thing. So as you can see right now, this piece of aluminum foil isn't doing anything on it, just looks like a shadow. So let's cool it down with this liquid nitrogen we were using before. And you can see it fall down very clearly. And let's heat the other side up, why don't we? Because this does look very pretty as well, aside from being very useful. And let's take the candle away. And
now it's not anymore cold, as we can see.
Yeah, So,
But I think we are running out of time, only half a minute left. So,
quick one.
finally, we need to go back home, of course, and we need to use a plane to get there. Getting here, we had a lot of trouble with our planes, a lot of strikes going on with aeroplane companies. So, the last thing that we need is our home plane to actually fall down. So, like right here, I have an aeroplane wing, and as Oskar mentioned before, Schlieren imaging can be used to check how aerodynamic different objects are. So, here I have also a hot jet of air, and if I pass it through over this airplane wing, we should be able to see whether or not the wing actually works. So, let's check it out. And as you might have noticed, different colored areas appeared on top and on the bottom of the wing, showing us where a high pressure area and the low pressure area is. And this means that this plane wing actually works and we can use it to fly back home. So, we were Teadusbuss. We thank you all for listening to us and hope to see you in Estonia during the next Science Me.